Hi boys and girls, this is lecture 1.3 in unit 1. The topic of this lecture, linear functions. Before we begin, notice I've provided this helpful little symbol for you once again so that we are reminded that we will not be availing ourselves of an external calculator at this point, not for this lecture, not for the associated assignment. It is coming though, boys and girls, just to let you know the graphing calculator will be back in your hands in a very short period of time, but not yet. A linear function is an equation in two variables which can be graphically represented in the coordinate plane by a straight line. We should not find this surprising. After all, the word line is contained within the word linear, so we're not surprised to see that the graph of a linear function is a straight line. The equation of a linear function can be written in the form y equals mx plus b. And when the equation is in this form, the letter m represents the slope of the line and the letter b represents the y-intercept of the line. So here is a picture of a line where the y-intercept is labeled. Notice that the coordinates of the y-intercept, 0, b, whatever number that is, in this case it looks like a 2. Rise over run is the slantedness of the line, the slope, and it's a ratio of the change in vertical distance over the change in horizontal distance. That's why rise is in the numerator, run is in the denominator. That ratio represents the slope of the line. Let's graph a couple of lines. Why not? It's been a while, right? Well, this equation is in slope-intercept form, so because it is arranged this way, we know that the slope of the line is that number -2/3, and we know that the y-intercept is 5. We can use this information to help us graph the line. The y-intercept is the place where the line must cross the y-axis. It's telling us that happens at 5. So we sort of now pin the line to the coordinate plane by saying it must go through 5. Now I'm using this line here to show you that there it is, pinned to that place. At this point, all we know is it goes through that point. We don't know the slantedness of the line. We just know that it goes through the point 0, 5, which we have drawn here. But using the slope now, since the slope is -2/3, it means from that dot, if I go down 2 units over 3, I find another point on this particular line. Now, not only do I know where it is pinned to on the y-intercept, I know another point that it goes through. And so with the y-intercept and the slope, I'm able to graph the line. There you have it, boys and girls. Now let's do letter B. Notice this one is not arranged very nicely for us in y equals mx plus b form. Let me change colors really quickly here. But I can certainly use my algebra skills to rearrange this equation in slope-intercept form. I know that the y term should be on the left side of the equation, so I use the additive property, once again so helpful having those properties of equality, to move that term over to the left side. Notice it's not like terms with anything. I'm just going to write it next to the -3/4 x that was over there. Of course, the x term in the template that I'm going for is on the right side of the equation. So let's move that over. Once again, just using algebra skills or rules of equality, properties of equality to do the things that I need to do. This leaves 1/2 y equals, let's make sure that we're putting the x term in front of the -1 since that's how it's arranged in the slope-intercept form of the equation. So now I have 1/2 y equals -3/4 x minus 1. I'm one step away from having y equals, instead of 1/2 y, I need y. So I'm going to multiply everything in the equation by 2/1. Again, a legal move according to the properties of equality. This gives me now y on the left side. On the right side, we have 2/1 times 3/4. This cancels, giving me 3/2 x. I hope that's not too messy. And then -1 times 2 is -2. There is the equation of the line that we were looking for. With this information, I can now graph the line. Let's use the y-intercept first. Obviously down here at -2. That means I can take the line and pin it. Now, of course, you don't have this handy little tool which allows you to just move a line around on your coordinate plane, but I, of course, am using this for demonstration purposes. Let's go ahead and say there. We know you're there. Now, the slantedness will come from the slope, which is 3/2. And both of those numbers positive, indicating a positive vertical direction, a positive horizontal direction. So from here, I'm going to go up 1, 2, 3, 1, 2, 3, over 2. I almost had it, which gives me another point on the line. So now not only do I have it pinned in the correct place to the coordinate plane, but I have the correct slantedness as well. And there's the graph of that line. Good practice. Now let's talk briefly about domain and range. To be honest, for a linear function, it's nothing really that earth-shattering. A linear function graphically depicted by a line, if you think about it, since we know that the line actually goes on forever in both directions, the domain of any line is ultimately going to be all of the real numbers. Isn't it true that eventually we'll use all of the x values and all of the y values in creating this line? Technically, the range of this function also is all real numbers. Again, eventually, in creating this line, we'll use all of the y values in both directions. However, often when graphing a line, you'll see a table of values or perhaps a list of ordered pairs. And when they ask you for the domain and range, when you're given that information, the x values are the domain and the y values are the range. Another word for x values, often when you're talking about a function, is input values, and range would be output values. Function notation is a useful way of writing linear functions, and the following two statements are equivalent in meaning. So we have seen this before, y equals negative 2/3 x plus 5. F of x equals negative 2/3 x plus 5 means the same thing. Y is an output value, f of x is an output value. F of x has a practical function because we can say things like, what is f of 2? And that's understood to mean that you plug 2 in for x to get the output value. So that's why we see function notation. Now let's use a few domain values, input values here, and generate some output values as well. I'm going to use multiples of 3 because immediately each x value is multiplied by negative 2/3, and I just want to make this easy on myself. So let me put in negative 3, 0, and positive 3. When I put negative 3 in as 3, or these three values in as 3 input values, now that actually means I'm asking for f of negative 3, f of 0, and f of positive 3. That means put those numbers into the function and get the output values. When I put negative 3 in for x here, I get negative 2/3 times negative 3, which is going to be a positive 2 plus 5 is a 7. When I put 0 in for x here, 0 times anything is 0, plus 5 is 5. And when I put 3 in for x here, 3 times negative 2/3 is negative 2 plus 5, which is 3. Therefore, the ordered pairs associated with this, 3, 7, 0, 5, 3, 3. If I graphed these, of course, it would form the line that would be expected from this equation. And if I were asked to name the domain out of this set of ordered pairs, I would say negative 3, 0, and 3, the range 7, 5, and 3. Now let's discuss slope a little bit more. We already said that slope is the ratio of vertical change, otherwise known as delta y, or rise, to the horizontal change, delta x, or run. The formula to find slope is delta y over delta x, rise over run, or y2 minus y1 over x2 minus x1. Because notice in this little diagram here, if these are the ordered pairs of the 2 points that you're given, delta y would be the change in y values, which would be found by subtracting the 2 y coordinates, whereas delta x would be the change in the 2 x coordinates found by subtracting them. So this is the formula that you probably already have memorized. Slope refers to the slantedness of the line, and it can be positive, negative, 0, or undefined. If the slope is positive, then the line is going to go up from left to right. If the slope is negative, it's going to go down from left to right. If the slope is 0, you're going to have a horizontal line, and if the slope is undefined, meaning there would be a 0 in the denominator of the fraction, you would have a vertical line. Now let's look at some special graphs, starting with a horizontal line. The equation of a horizontal line is shorter than what we're used to. It's just y equals b. B is the y-intercept, and it will be some number. For example, y equals -3. Notice the graph of the horizontal line here, y equals -3. Similarly, with vertical lines, a shorter equation as well. X equals a. A is the x-intercept, and it will be some number. For example, x equals 2. And here is the equation of the vertical line, x equals 2. Often when we see something like this, we might not understand that it's an equation of a line because it's not in the form that we're used to seeing. But we need to train ourselves to recognize that this isn't just saying that some y is equal to 5, that it actually is an equation, just as this is an equation of horizontal and vertical lines. Piecewise functions are functions that use different formulas for different regions of the domain. And I have to be honest, these are kind of fun to graph. It's as if you get several functions for the price of one. Notice this function is saying, let's be 2x when x is less than or equal to -2. But then let's be 1 when x is between -2 and 1. And then let's be -x plus 2 if x is greater than 1. The easiest way to graph these is to divide the domain, the coordinate plane, into the regions that are dictated by the domain listed here. Notice in the domain we have a section that's less than -2 over here, a section that's between -2 and 1, that's this section, and then of course a section to the right of +1, which is here. And so what we're going to do is we're going to graph in the left section the function y equals 2x. In the middle section, we're going to graph y equals 1. Of course, that's a horizontal line, as we just saw up here. And in this section over here, we're going to graph -x plus 2. So when we figure out how to do this, what we're going to do is carefully determine in each section how we would graph our function. Let's start with 2x. Since it begins at -2, then what is 2 times -2? Turns out that function value is -4. Now notice that it's inclusive, so if that were just less than -2, we'd put an open circle there. But since it's less than or equal to, we put a closed circle. Let's use -3 in our function. 2 times -3 is -6. Put -4 in, we get -8. And so in this section, we want to graph this function. Now, I've already prepared these lines just primarily for neatness and speed. Wouldn't it be nice if you could just drag some little lines over there as well? But it'll be slightly different for you. Now, of course, in this middle section, this is kind of easy. We're going to graph the horizontal line, y equals 1. But notice that on the left side, it's an open interval. So it's going to be an open circle here, a closed circle here. I kind of missed the mark. Let me do a little bit better on that one. It's going to be an open circle here. Maybe that's better. All right, and of course this little red line is the piece I'm going to use. Move it into place. And finally, for the section that is on the right, to greater than 1, we're going to use -x plus 2. So we wonder, what is this function when x is equal to 1? -1 plus 2 is 1, so it also starts here at 1 comma 1. What happens when I put 2 in for the function? -2 plus 2 is 0. What if I put 3 in for the function? -3 plus 2 is -1. So for that section of the graph, I have that function. And that is how you graph a piecewise function. Now in this next section, we're going to graph absolute value functions and transformations. Now just ignore the strange diagonal lines that are all over the screen. As you have probably guessed, these are going to help me graph my functions later. But first, let's start with y equals the absolute value of x. This is the parent absolute value function. The vertex is centered at 0, 0, and you can see it's kind of got a slope of -1 and +1 in both of its little v parts. Let's look at a table of values to understand why this is a v shape. And I'll just choose -2, -1, 0, 1, and 2 for some sample x values. Plugging those into the absolute value function, the absolute value of -2 is 2, of -1 is 1, 0, 1, 2. If I plot these points, -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. That's where the classic V shape comes from. Now let's look at this second function down here, y equals the absolute value of x minus 2. I wonder what effect this minus 2 is going to have on the absolute value shape. Let's try the same values and find out what y values go along with it. Absolute value of -2 is 2, 2 minus 2 is 0. Absolute value of -1 is 1, 1 minus 2 is -1. When I put 0 in, I get -2, 1 gives me a -1, and 2 gives me a 0 again. Let's plot these points. -2, 0, -1, 1, 0, -2, -1, -1, and then 1, -1, and then 2, 0. So this graph, notice it looks very similar to the parent function absolute value graph, but it is shifted down 2 units. Let me find this little fellow. Oops, nope, just him. There we go. And I wonder if we can make some sort of connection about the -2 that was here and the vertical downward shift that we see. And of course, yes, you can. That is going to affect the parent function by shifting it vertically on the y-axis. Let's look at the purple graph and see what effect this +1 is going to have. Again, I'm going to choose the same 5 ordered pairs, the same 5 x values, -2, -1, trying to keep the color theme consistent here. If I put a -2 in for x, -2 plus 1 is -1, the absolute value of which is 1. -1 plus 1, 0. 0 plus 1 is 1, the absolute value is 1. This becomes 2, this becomes 3. Let's plot these points. We get -2, 1, -1, 0, 0, 1, 1, 2, and 2, 3. Interesting. Are we surprised by this? Maybe not, boys and girls. Maybe you remember your absolute transformations, absolute value transformations from Algebra 2 or Algebra 1 or wherever you studied them. Let me just make sure this is right. There you have it. Now, the connection that you're supposed to make here is that notice inside the absolute value bars, if there is a number in addition to the x, then it represents a horizontal shift, but of the opposite direction of the sign. +1 shifted as left 1 unit. Now, that brings us to a general topic of transformations in the absolute value function. You could have a plus or minus, which would indicate an upward V or a downward V if it were negative. That is a reflection. You could have a number in front of the absolute value bars, and that would indicate a dilation. It would make the absolute value graph narrower or wider. In here, as we've already discussed, we would have a horizontal shift left or right, and out here a vertical shift up or down. So with this knowledge of these kinds of transformations, let's graph this without a set of ordered pairs, just with our knowledge of what is going to happen when we use the transformations. The regular graph, or the parent graph, 0, 0, and a slope of 1 to 1 would be here. But this horizontal shift and this vertical shift is going to change the position of the vertex. So let's move it. This +1 would mean shift left 1, and then the +3 on the outside means to shift vertically up 3 units. That's where the new vertex is. Now the negative means it's going to be a downward facing V shape, and outside here there's a 2 instead of no number, and so that means instead of a 1 to 1 ratio, it's a 2 to 1. So we can kind of use that as a slope. If I go down 2 over 1 in both directions, I get the slope of my new V shape. So using these handy little lines that happen to be sitting out here, I can now graph my new transformed absolute value function just based on my knowledge of the transformations inherent within the equation. Good job, boys and girls. Okay, now we're going to switch gears a little bit from graphing to writing equations of lines. We've already discussed slope-intercept form, y equals mx plus b, where m is the slope of the line, b is the y-intercept, but there are also a couple of other forms of lines that you may see. Point-slope form, which is y minus y1 equals m times the quantity x minus x1. M is the slope, and x1, y1, these ordered pairs, represent a point on the line. Point slope form is handy when you know slope and a random point on the line rather than just the y-intercept. And then finally we have standard form, ax plus by equals c, and notice that these are some secret codes that if you know them you can get from standard form the slope and the y-intercept without rearranging it into y equals mx plus b form. The slope is negative a over b and the y-intercept is c over b. Now, using these three forms of an equation, we can write equations of lines. But what are the clues? Sometimes you will be asked to write equations of lines given the slope and the y-intercept. If that happens, use y equals mx plus b, just plug in your given slope and y-intercept for m and b. That's like Christmas. If they give you m and b and ask you to write an equation of the line, bam, you have it. Or another set of clues you might be given, slope and a random point on the line. Here's where you're going to use point slope form, plugging the slope in for m and the random point in for x1 and y1, and then you can rearrange that equation into slope-intercept form. What if you're given 2 points, no slope at the beginning, just 2 random points? Well, first you will find the slope using your 2 given points in the slope formula. Remember the slope formula, y2 minus y1 over x2 minus x1. Once you have the slope, go back to point slope form, putting the slope that you found in for m and use one of the points you were given for x1 and y1, rearrange into y equals mx plus b form. Or you could be given a point and told that your line is parallel to another line. Well, parallel lines have the same slope. So you can look at the line you're given, figure out what the slope is of that line, and then you know that since your line is parallel, that it has the same slope. So once you've extracted the slope from the parallel line that you were given, go ahead to point slope form, plug it in for m, use the point that you were given for x1, y1, rearrange into slope-intercept form. Now, the last set of clues that you could be given is you could be told that your line is perpendicular to another line. Perpendicular lines have opposite reciprocal slopes. So you can look at the line that you're given, knowing that you're perpendicular, extract their slope, change it by making it opposite reciprocal. That, of course, means that's your slope. Plug it in for m, use the point you were given, x1, y1, rearrange into slope-intercept form. So with these three forms of equations and knowing what to do, no matter what set of clues we're given, let's try this out. First of all, letter A says, write an equation that passes through 5, negative 2, and 2, comma 10. Ah, they gave us the set of clues, which is 2 points, meaning we're going to need to find the slope first. Remember the slope formula? y2 minus y1 over x2 minus x1. Therefore, for the numerator, we subtract the two y values. Remember that if the number is negative, you have to recognize that since subtraction is included in the formula, it's going to be the number minus the negative number. Over, in this case, let's subtract the two x values, 2 minus 5. This becomes 12 over negative 3, which is negative 4. Therefore, your slope is negative 4. Now you have a slope and 2 points, but we can use point slope form, y minus y1 equals m times x minus x1. It doesn't matter which point you use to plug in here. Let's just use 2 comma 10. I'll have y minus 10 is equal to the slope negative 4 times x minus 2. Now technically this is a form of an equation, but if they want the answer in slope-intercept form, it's 2 short, easy moves to get it into slope-intercept form. First, distribute the slope. This takes us to y minus 10 equals negative 4x plus 8. Then move the 10 over, and you end up with y equals negative 4x plus 18. There you have it. All right, we successfully navigated this set of clues. I wonder what's coming next. Write an equation that passes through the point negative 2, 3, a point, and is parallel to the line 4x minus y equals 1. Well, remember, parallel lines have the same slope. So whatever the slope of this line is, that would be the slope of my line as well. So we need to extract that information from this line. This is in standard form, and if you remember the secret codes, let me change colors here. M, the slope of a line in standard form, is negative a over b, and the y-intercept will be c over b, and this is a, b, and c. Therefore, the slope of this line is going to be negative 4 over negative 1, which is 4. We don't really need the y-intercept, we just need the slope, because since we're parallel to this line, that is our slope. Now we have slope and we have a point that's given to us. We're going to use point slope form. Y minus 3 is equal to 4 times x minus a negative 2, which will be x plus 2. Again, two short, easy moves to get it into slope-intercept form. This is 4x plus 8, and then add the 3 over for your final equation in slope-intercept form. Y equals 4x plus 11. All right, we're back with systems of linear equations. I know this video lecture is a bit longer, boys and girls, and I apologize for that, but this is our last topic. A system of two linear equations in two variables, x and y, also called a linear system, consists of two equations, which can be written in the form ax plus by equals c. System simply means more than one. And of course, linear equations are lines. So now we're talking about two or more lines graphed at the same time. A solution of a system of equations is an ordered pair, x comma y, that satisfies each equation, meaning that point is on both lines, or if there were more than one, on all of the lines. Solutions correspond to points where the graphs intersect. So in this particular diagram, line A and line B comprise a system of equations. The ordered pair, 1 comma 2, is the solution. However, drawing two lines in the coordinate plane doesn't always produce intersecting lines. They can intersect in one point, in which case you would have one solution, and the coordinates of that ordered pair would be your answer. But the lines could also be parallel lines. If so, then they don't intersect at all. And if we have defined a solution to be where the lines intersect, then we would say there are no solutions when these lines are parallel. They could also be the same line. Maybe the equations didn't look the same, but when you graphed both lines, it turned out to be the same line. In that case, they're intersecting at every point, and there are infinitely many solutions. So your three options for a solution to a system of linear equations: one ordered pair, one xy value, or possibly no solution, or possibly infinitely many. Now let's solve a system of linear equations using three different methods. Graphically, simply graphing the two equations and visually determining what the solution is, and then two algebraic methods, elimination and substitution. Well, to graph these two lines, we're going to need to know what the slope and the y-intercept are. Since they're both in standard form, we have the option of rearranging them into slope-intercept form to get this information, or using the secret codes. So let me write down the secret codes once again. The slope is negative a over b, and then the y-intercept is c over b. So for each of these lines, let's get that information. Starting with the first line, negative a over b is going to be negative 4 over 1, which is negative 4. The y-intercept, c over b, is 8. Then for the second line, the slope is going to be negative 2 over negative 3, which is a positive 2/3. The y-intercept, 18 over negative 3, which is negative 6. Now let's graph each line, putting it into place. The y-intercept of the first line is 8, and then negative 4 over 1 takes us to this location. Fortunately, there's a handy little green line here, just waiting to be used in this situation. Now let's graph the blue line. The y-intercept is negative 6. The slope up 2 over 1, 2, 3, which takes us here, And fortunately, we have at hand a blue line which we can put into place. Now notice that when these are graphed, you can visually see that the solution, the place where they intersect, is the point 3 comma negative 4. Now you probably have seen situations where it is not so easy to see the point of intersection. What if the solution was something like 3 and 1/3, comma 4 and 2/7? You would just be estimating the solution at that point. That's why it's great to have these algebraic methods. Let's start with elimination. Elimination says add these two equations together in such a way that one of the variables is eliminated completely. Well, as the equations are right now, adding them together will not eliminate any variable. So we have to manipulate one of the equations first, or possibly both of them. In this case, though, if I just multiply this top equation by 3 everywhere, remember I'm allowed to do it as long as I do it to both sides of the equation, and rewrite it down here, I get 12x plus 3y equals 24. Now when I add the two equations together, the y variables cancel completely. This gives me 14x equals 42. Dividing by 14, the x coordinate of my solution is 3. Now I can use that in one of the original equations to solve for the y coordinate. I'll just use the first equation. 4 times 3 is 12, and when I subtract that from 8, I get negative 4. So notice my algebraic method verifies what I got graphically before. Now let's practice the substitution method. In this method, we choose one of the 4 variable terms, it doesn't matter which one, and solve for that variable. Now, you can choose any of the 4 variable terms and solve for the variable, but there are some variables that are easier to solve for than others. If you have a variable that has no coefficient, for example, this y, this is going to be easier to solve for because you don't have to divide by the coefficient. So let's solve for this y. This is our choice. In subtracting 4x to the other side, we find that y is equal to 8 minus 4x. Let's take this value for y, plug it in for y in the other equation, substitute it for y in the other equation. We get 2x minus 3 times 8 minus 4x, the substituted expression, equals 18. Now, as you can see, this is an equation in one variable, and we will be able to solve it. 2x minus 24 plus 12x equals 18. These are like terms, so 14x minus 24 equals 18, 14x equals 42, which means x equals 3. Again, that of course is the x coordinate of your ordered pair. If I plug 3 in here now, I get 8 minus 12, and negative 4 is the y value. We of course are not surprised to see that we got the same solution using all 3 methods. That's it for today's lecture, boys and girls. I leave you with an inspiring quote by Oswald Veblen. 1924, I'm not sure if that's when he was born or when he died or when he said this, but here's the quote. Mathematics is one of the essential emanations of the human spirit, a thing to be valued in and for itself, like art or poetry. I hope you agree, boys and girls. And let me show you another mathematical beauty before we go. Ah, fractals. Aren't they amazing? God bless you, boys and girls.